Last class, I have introduced the concept of random variables. Okay. And we have seen that it is a function defined on the sample space and it takes real values. Okay. So now we will see types of random variables. Okay. So the random variables are classified according to the values that they take. So you have seen that, for example, I considered, uh, say, if we toss a coin, then we look at the number of heads, or if you toss a dice, you look at the outcome, or you look at the sum if there are two dice. So certain values are taken, isn't it? When the values are finite or countable, then it is said to be a discrete random variable. On the other hand, you can have random variable as time, weight, length, age. If we have values being taken over an interval, then it is said to be a continuous random variable. Okay, so I give the definition here. So if you have like number of wins in a series of games, number of children in a family, number of deaths in a hospital, number of wickets taken by a bowler, and so on. So these are all examples of discrete random variables. Okay. Now, if the value is taken over an interval, for example, length of a string, age of a person, life of a bulb, etc. So these are all examples of continuous random variables. Okay. Now, depending upon the type of random variable, you will have the description of the probability distribution different. it will not be same. So let me talk about the probability distribution now. To describe probability distribution of a random variable, probability mass function. If a random variable x is discrete and it takes values x1, x2 and so on. So it belongs to certain set. Let me put it a script x, okay, and its probability distribution is described by a function called probability mass function, okay, that is PMF. Px satisfying the following conditions. The conditions are: one, that probability of x is equal to xi, it is the Px xi for xi belonging to x, okay. Second is that since it is a probability, this will always be lying between 0 and 1. And the third is that the sum of the probabilities is equal to 1. So if there is a function which satisfies these three properties, it is said to be a probability mass function of a discrete random variable.
So can you show the definition once more?
Yes. So first of all, we have two types of random variables. One is called a discrete random variable and another is called a continuous random variable. If the random variable takes a finite or countably infinite number of values, then it is said to be a discrete random variables. So for example, we count the number of heads, the number of wins, the number of children, and so on. So number of students. So whenever we do this kind of counting, this can be finite or countably infinite, then it is said to be a discrete random variable. Now there is another case where the random variable can take values over an interval. So if I am considering, say, length of something, age of a person, the life of a bulb, so these things are measured over an interval. For example, if I say length, so length you can say it is 10 centimeters, then somebody can be more accurate, it will be saying 10.3 centimeters, then somebody is more accurate, he will say 10.32 and so on. So it is the value taken over an interval. Similarly, the life, so it is measured in months, then you can put more accuracy, then months, and then days, and then hours, then there is a minutes, then there is a second, and then there can be more parts of that. For example, time to complete a race, and so on. So then it is said to be a continuous random variable. So now next question comes, what is the purpose of studying the random variables? Because initially we had the sample space, the outcomes were collected in a sample space. From random experiment we go to the sample space, and then we associate the probabilities with the outcomes of those sample space. So we have event space, and based on that we defined a probability function. Now that probability space, that omega BP, it has been transformed to R, C and Q, I wrote in the last class. So what is that Q? That means how the probability is assigned to values of the random variable. So for that we have two cases. If the random variable is discrete, then it will take some values x1, x2 and so on. Okay, it could be finite or it could be infinite. So you can have x1, x2, xn, or it can go on. So I have just written x1, x2 dot dot belonging to certain set script x. So the probability distribution of the discrete random variable, it is described by a function called a probability mass function. And now you can see here that it is defined like pxxi, that is what is the probability of x equal to xi, that is pxxi. And then we have, since it is defining the probability, it should lie between 0 and 1, and the sum of all the probabilities must be equal to 1. So this is the definition of the probability distribution of a discrete random variable. It is called a probability mass function. So let us start with a very simple example so that the concept will become absolutely clear, something which you already know. So I will try to explain through a very extremely simple example. Is this definition clear to everyone?
Yes, sir, it is clear.
So I will take a very simple example. Consider tossing of two fair dice. Okay. So let us define, say, x to be okay. So x is the random variable defining the sum. So what are the values this random variable will take? X can take values 2, 3 and so on up to 12, because in the dice you have faces 1 to 6. So the sums can be 2, 3 and so on up to 12. So what is the probability distribution of this? Okay, the PMF of x. So you will have px2, that is probability of x equal to 2. Now this is corresponding to the outcome 1, 1, which has the probability 1 by 36. What is the probability of x equal to 3? This is corresponding to outcomes 1, 2 and 2, 1. So it is 2 by 36. What is the px4? So that is 1, 3, 3, 1 and 2, 2. So it is 3 by 36. And like that, you can write down all of them. This is a complete description of the probability distribution of this random variable x here. And I hope it is very clear to all of you, because this problem you already know, tossing of dice. So it is just the conversion into the probability mass function. So it must be clear to all of you. Is that okay?
Yes, sir, it's okay.
Okay.
Yes, sir.
So, I mean, this is a very, straightforward kind of understanding. In the discrete case, the correspondence between the random variable to the probability mass function is determined just by the original assignment itself. So, let us take, say, another exercise. Okay. I think let us put it straightforwardly. So 5 ATMs in an office. So for example, if you look at our SBI, so if you go outside, there are 5 ATMs there and 2 are working. Okay. So you randomly choose So let me generalize this one rather than conversion of this problem to a random variable. So what we do, we put it like this. Okay. Suppose he selects 3 machines, and then now out of that there can be defective and there can be non-defective. Let x be the number of so you have to find the probability distribution of x. So what are the possible values of x here? You have the collection that there are total 5, and out of that you have 2 working machines and 3 are non-working. Okay. And there have been 3 selections. So it could be that none of them are working, it could be one is working, or it could be that 2 are working. So let us look at the probability distribution here. What is probability that x is equal to 0? So can anybody tell here? This is a very simple problem. Yes. Can anybody tell this?
One upon 5C3.
See, if I am saying none of them are working, that means in the three selections, the three that have been selected, okay, all of them are not working, isn't
Yeah,
it? So it
yeah.
is 3C3, that is 1, okay?
1 upon
And
10.
in the denominator, you will have that there are 5, out of that you have chosen 3,
5C3.
okay? So if you simplify, this is becoming 1 by 10. Now, what is Px1? So similarly, you should tell. That means 2 are not working and 1 is working. So that is becoming 6 by 10. And what is Px2? That means 3C1, 2C2 divided by 5C3. That is equal to 3 by 10. So if I write here the distribution, it is Px0 is 1 by 10, Px1 is 6 by 10, Px2 is 3 by 10. So this is the probability distribution of this random variable here.
So here, why aren't we considering the sequence of the choosing of the machines?
Yeah, because this is not required here, because this is a selection, isn't it? So in the selection, the order does not matter. Here the order does not matter because we are looking at the number of working machines. Okay. So it doesn't matter. The order does not matter here. Okay, so this description of the probability distribution is clear.
Yes, sir.
Okay. Now let us go to the continuous random variable. Now in the case of continuous random variable, the probability distribution is defined in a different way. The probability distribution of a continuous random variable x is described by a probability, and I am changing the name, it is called probability density function. Okay, and it's satisfying this is a non-negative function for all real values. Second is that the integral of the density function is 1. And the third is that probability of any interval is evaluated by integrating the density function over that interval. So there is a difference. Earlier I had said P, that is the probability mass function, it lies between 0 and 1. The sum of the probabilities is 1, and the probability of a point was the probability mass function at that point. In the case of continuous random variable, the upper limit I have removed, it is only non-negative function. However, the integral of the function must be equal to 1 if we integrate over the whole range. And in place of the probability of a point, here we calculate the probabilities of intervals. So for example, what is the probability that a person will live between 60 to 70 years of age? What is the probability that say life of a bulb is between 30 to 40 hours? So it is like that. We can find the probability of interval. So there is a fundamental difference that you can see between the description of the probability distribution for a discrete and for a continuous random variable. Okay, so the names are also you can see that we have put the names as mass function and the density function. So that also is indicative of something. So can you see this pen that I am showing?
Yes, sir.
So if you look at this pen, so this pen is a like it has a density at each point, isn't it? Because it's a thick thing of a plastic or fiber, you can say, and so there is a density at each point. Okay, and if I consider it in a different way, suppose I consider it as a weightless string and I attach say certain weights here, okay, at each at several points. So suppose I put one this one, there is a weight at another point, say 3 places I have put certain weights here, okay, then it becomes like a mass function. At 3 different points I am putting I am attaching certain masses, okay, then it becomes a mass function. So that is the difference you understand between the probability distribution of a discrete and continuous random variable. So from physics you can understand easily that we can have masses or we can have a density. So if I remove it and I consider this as a this as a pen, I mean whatever, some metallic thing or something, then there is a density at each point which may change also. For example, there is a thinness here, it is thick here and it is more thick at the end here. Okay, so I hope this example makes the things very clear to you. Is this clear?
Yes, sir.
So let us consider some example. Suppose I consider fx is equal to say so if you look at this, this is a non-negative function. It is 1 by 3 for x lying between 1 to 4. What is the integral of this? From minus infinity to infinity. So it is 0 at the interval from minus infinity to 1 and from 4 to infinity, and between 1 to 4 it is 1 by 3. So it is 4 minus 1 by 3, that is equal to 1. So that means it is satisfying the basic properties of a probability density function. Actually, what is the kind of function? If you plot it, it will look like this. Between 1 to 4, this is taking value 3. Okay. So if I put x on this side and fx on this side, then this is the kind of distribution that I have described here. So if I want to find out what is the probability, say 2 less than x less than 3. So this is integral of 1 by 3 over the interval 2 to 3. So that is equal to 1 by 3. So in the case of a continuous random variable, you can evaluate the probabilities of all the intervals, but you cannot calculate the probability of a point. In fact, the probability of every point will be 0. Let me take another example. Over the interval 0 to 1, I define the density function to be 2x. So it is something like this. If you have the interval 0 to 1, so if you consider the integral 2x, it is equal to 1. It is a non-negative function. If I want to calculate the probability of an interval, suppose I say what is the probability 1 by 4 less than x less than say 1 by 3, then it is integral 2x dx over 1 by 4 to 1 by 3, that is equal to 1 by 9 minus 1 by 16, that is 7 by 16. Another thing that you can understand here, that in the case of continuous random variable, the probability of every point will be 0, because the probability of an interval is defined to be integral over that. So when you consider an interval, whether you include the end point or not, it does not make any difference, because integral does not change the value. When I say, for example, 1 by 4 to 1 by 3, okay, so this is this area. If I am looking at this particular area, of course, under this particular curve, then whether the end line is included or not, it does not make any difference. So for a continuous random variable, the probability of a point is 0. That is probability that x is equal to c is equal to 0 for all. So is that okay?
Yes.
Yes, sir.
And you can also associate it with the description that I gave you of a pen actually. So there is a density at each point, but if you want to find out the mass at each point, then the mass is not defined there, isn't it? In physics, that is what happens. The mass is defined only if you attach separate masses there. So you have two descriptions here, one for the probability mass function and another is the probability density function. So there is a general function which actually takes care of both of this, and it is slightly generalized function. Let me give the definition for that. That is called the cumulative distribution function of a random variable. So I give a new name here for a random variable x. The CDF f is defined as, so it is capital F now. Okay. Probability of the set that the set of all those sample points for which the random variable takes values less than or equal to given value is small x. So there is a, I am using capital X and small x together. As already mentioned to you, actually we are using the name of the random variable by capital English letters, capital X, capital Y, and so on, capital Z, U, V, W. Later on you will see all those utilizations. And the values taken by the random variable, they are denoted usually by the small English letters. Okay, so small x. In popular terminology, see, we will just write like this: probability of capital X less than or equal to small x. Okay, but actually, if you consider the proper description, it is the, because probability p function is defined over a sample space. So therefore, it is the set of all those points for which x omega is less than or equal to x. Now, how is this function useful and why we define this thing? So let me talk about this now. First of all, this function has certain very nice properties. What are the properties? First property is that limit of fx as x tends to minus infinity, that is 0. So this function goes to 0 as x tends to minus infinity. And the proof is not difficult to anticipate here. See, as x tends to minus infinity, the area under which you are calculating the probability, that is the region where you are looking at the values, it shrinks and ultimately it becomes an empty set, because you are saying x tending to minus infinity. And since the random variable is an assignment to the real values, so if you say x tending to minus infinity, then there are no points in the sample space left out. So it will become 0. Then limit of fx as x tends to plus infinity, that is 1. So again, if you see as x tends to infinity, then all the points of the sample space will be included. So the probability must become 1. The third property is that if x1 is less than x2, then f of x1 will be less than or equal to f of x2. Again, you look at this definition itself. See, if I am considering 2 points, see, suppose this is x1, this is x2. Okay. So if I say x is less than or equal to x1, then this is the probability. If I say x1 is less than x2 and I am looking at probability of x less than or equal to x2, then I have added some more points. If I am adding some more points, then if some of them have a positive probability, then fx2 will become greater than fx1. Even if they don't have any probability, then fx2 will be equal to f of x1. So in general, f of x1 will become less than or equal to f of x2. That is, f is a monotonic non-decreasing function. And the next property is that f is continuous from right at every point. that is limit of fx plus, which we generally write like this, h tending to 0, that is equal to fx. That is because of the way that we have defined. We have defined actually x less than or equal to x. So from the right hand side, if we approach, then x less than or equal to x, the value at this point will be same as the limit that is at that point. So that is the function f is continuous from right at every point. Now this function is actually a very nice function in the sense that given a random variable you will have a CDF, and if there is a function which satisfies these 4 properties, then it is CDF of a random variable. Okay, so this is one-to-one correspondence. So let me see, conversely, if a CDF, if a function f satisfies the above 4 properties, then it is CDF of a random variable x. So first thing is that we defined the CDF, the PMF and the PDF. Is there any relation? The answer is yes. So if x is a discrete random variable, then the relationship that is fx is equal to sigma px xi less than or equal to x. That means we add the probability mass function over those values of xi which are less than or equal to x. And conversely, you will have the relation that if I am given the capital F, then I can determine the probability mass function also. And we can write like this, that pxxi is equal to fx xi minus fx xi minus 1. This is the relation. In the case of continuous random variable, if we integrate the density function from minus infinity to x, I will get the CDF, and conversely, if I differentiate the CDF, I will get the PDF. So in both the cases, whether you have discrete or continuous, there is a nice relationship between the functions here. Now let me just go to some practical examples so that it becomes very clear.
Sir, why
So
have
let us look
we
at,
written for almost all x? Like, why it is not true for all the x?
yeah, that is true. So that's a good question, but I don't know whether you have done this much of, have you done the integration? Theory of integration, have you done? Any
Yes,
students
so
who
we
are
can
there who
relate.
have done theory of integration? What? Theory of integration have you done? I mean,
No, sir.
not the calculation of integrals. I am asking the theory of integration. Have you done the theory
No,
of
sir.
integration?
No, sir.
So there is a small technical detail here. Actually, when we define this function, so actually the definition that I have written minus infinity to fx t dt, actually it is the Riemann integral actually. And if we consider Riemann integral here, it is absolutely continuous function. So there is a small difference. You have done the continuity, but have you done, I mean, of course, I think because you have done only maths 1 and maths 2. Only the students of mathematics department, they will be doing real analysis course. So there is a formal definition of the integral. So you have Riemann integration, and of course you have Lebesgue integration. And so there is a small thing. I mean, like you have continuity, but continuity is not the strongest thing. And of course, you know that if there is a function is differentiable, then it is continuous. Okay, but every function which is continuous need not be differentiable, isn't it? So there is a continuity is a weaker thing, and differentiability is a stronger thing. But in between there is something, it is called absolute continuity. Okay, so absolute continuity allows for some points there, okay, where the function may not be differentiable. So here this capital F is actually absolutely continuous function. That means it may not be differentiable at some of the points. And this almost all simply means, so there is a small technical thing. That means those points can be ignored. I mean, that means suppose I am talking about intervals. Then in the interval, if I remove finite number of points, then it won't make any difference because the density at those points is 0. So that means there is no probability associated with that. So this almost everywhere condition or almost all condition actually relates to that. So that means for all practical purposes, it's all right. That means if you differentiate the density function, you will get the, if you differentiate the CDF, you will get the probability density function. But I will not get into too much of technical details here because that is part of the real analysis and the major theory and integration courses, which is taught to the mathematics students. So I just written it because I want to be technically correct. So I have written for almost all x. Okay. So let us look at some of the exercise. So we did, for example, the dice throwing problem. Okay. So for dice problem where x was the sum. Okay. So let us look at what will be the description of the CDF. So there the first value that the random variable took was 2, isn't it? 2, 3 up to 12. So the CDF is 0 for x less than 2. Then at x is equal to 2, it became 1 by 36, isn't it? Because probability that x is equal to 2 was 1 by 36. And the next value that the random variable took was 3. So between 2 to 3, that is 2 less than or equal to x less than 3, this capital F will remain 1 by 36. Then at x equal to 3, the probability was 2 by 36. So this will become 3 by 36. 3 less than or equal to x less than 4. At 4, the probability was 3 by 36. So this will become 6 by 36. At 5, if you remember, it was 4 by 36. So it will become 10 by 36. At 6, it was 5. So it becomes 15 by 36. Then at 7, it was 6 by 36. Then at 8, it was 5 by 36. At 9, it was 4 by 36. At 10, it was 3 by 36. At 11, it was 2 by 36. And at 12, it was 1 by 36. So this is the complete description of the cumulative distribution function for the random variable, which was described as the sum of the outcomes on the two dice. Suppose you are given this function only and you are not given what is the random variable or what is the probability mass function. Can you describe the random variable from here? Let us look at it, what kind of function it is. So if you look at the plotting of this, okay, let us consider the plotting of this. At 2, you are having 1 by 36. Then at 3, it is 3 by 36. So you look at this. Then at 4, it is 6 by 36. And so on. At 5, okay, and finally it is becoming 1. See, after 12, it is becoming 1. So you look at, this is acting as a step function. It is looking like a staircase, okay, where the size of the step is actually the probability. See, for example, if you look at the first step from 2, the size of this is 1 by 36. And which is the probability of x equal to 2. The size of the step at the point 3, that is the difference between these 2 points, that is 2 by 36, which is the probability of x equal to 3. Similarly, if you look at the size of the step at 4, the step size is 3 by 36, which is the probability of x equal to 4, and so on. So the CDF of a discrete random variable is a step function. See, I described the properties of the cumulative distribution function. The last property was that the function is continuous from right at every point, but it is not mentioned that it is continuous from left at every point. So in the case of discrete random variable, it is not continuous from left at a finite or a countable number of points. And at those points where it is not continuous, the size of the discontinuity, that is the difference between the two consecutive values, that is the probability mass function value at those points. And the size of the discontinuity at finite or countably infinite number of points determine the probability mass function. Okay, so that's all. I mean, this is a very clear-cut representation of the probability mass function. You look at the other exercise which I did. The second exercise was that number of working machines. Okay. And there, what was there? You had px0 was 1 by 10. You had px1 was 6 by 10, and you had px2 is equal to 3 by 10. Now you look at the CDF here. So at x is equal to 0, the value is 1 by 10. At x equal to 1, the value is 6 by 10. So the CDF will become 7 by 10. Okay. This is 7 by 10. And then at 2, it will become 1. So if you plot it, it will look like this. So the description of the CDF is, it is 0 for x less than 0. It is equal to 1 by 10 for 0 less than or equal to x less than 1. It is equal to 7 by 10 for 1 less than or equal to x less than 2. And it is equal to 1 for x greater than or equal to 2. Is it clear? Is this exercise clear to you?
Yes, sir. Yes, sir.
Okay, so very nicely it comes here that in the case of discrete random variable, the CDF is nothing but a step function. And so that means it is discontinuous at a finite or countably infinite number of values. And the size of the step at those discontinuous points, or the size of the discontinuity at those points, is actually the probability mass function. Okay. So let us just take a break for 5 minutes. Then I will come to the description of the relationship between the PDF and the CDF and certain exercises there. Let's have a break for 5 minutes. Now let us consider this relationship for the continuous random variables. Okay, so let us consider the exercise that we have done earlier. Say fx was, say, 1/3 for 1 less than x less than 4, and it was 0. Is the sheet visible?
Yes, sir, the sheet is visible.
So here, see, fx is minus infinity to x ft dt. So if you look at this, the density is actually defined to be positive only on the interval 1 to 4. So if I have x to be, say, -3 or any value which is less than 1, then you are integrating only 0. So this will be 0 for x less than 1. Okay, or less than or equal to 1. It doesn't make any difference, whatever we put. Now, if x is greater than 1 but less than 4, then it is integral from 1 to x of 1/3 dt. So then it is becoming x minus 1/3. And if you consider x to be greater than or equal to 4, then it is integral of 1/4 1/3 dt, which is actually equal to 1. So if you describe then this CDF, it can be written like this: 0 for x less than 1, it is x minus 1/3. For 1 less than or equal to x less than 4, it is equal to 1 for x greater than or equal to 4. And now let us look at the inverse relationship. I had mentioned that d by dx of fx. So if you look at for x less than 1, then it is 0. For x greater than 4, it is 0. And for x between 1 to 4, it is 1/3. So it is 0 for x less than 1. It is 1/3 for 1 less than x less than 4. It is 0 for x greater than 4. Now let us look at this explanation of the point for almost all x. So you can see here that there is a problem at x is equal to 1 and x is equal to 4. Is the function differentiable at x equal to 1?
No, sir.
And is it differentiable at x equal to 4?
No, sir.
So I think the point which you had asked about almost all x is clear now, isn't it? It is actually differentiable everywhere except at these 2 points. But since it's a continuous random variable and there is no probability associated with this, so for all practical purposes, it's all right. So that is why we use the word for almost all x. Okay. So the density is, so then we write like this: 1 by 3 for 1 less than x less than 4 and 0 otherwise. Now the question about this almost all comes here. So whether I should use x is equal to 1 in the first part or x equal to 1 in the second part, or whether I should use x is equal to 4 in the first part or in the second part, it does not make any difference. Like if I put 1 less than or equal to x less than or equal to 4, then also it will have the same description. That means if I calculate the probabilities of any intervals, etc., there will be no change. If I want to say put 1 less than or equal to x less than 4, then also there is no change. If I want to put say 1 less than x less than or equal to 4, then also there is no change. And if I put 1 less than x less than 4, then also there is no change. So I hope this exercise is clear to all of you.
Yes, sir.
Is it okay? Let us look at the second one which I had given. 2x for 0 less than x less than 1, 0 for outside this interval. So again, if you look at minus infinity to x ft dt, then between minus infinity to 0, the density is 0. So this will remain 0 for x less than 0. Or we can put less than or equal to 0 also. It will not make any difference. And it is integral of 2t dt between 0 to x for 0 less than x less than or equal to 1. And it is equal to integral of 0 to 1 2t dt for x greater than or equal to 1. So this will become then 0 for x less than or equal to 0. This is x square for 0 less than x less than or equal to 1, and it is equal to 1 for x greater than 1. Here I can put say here I can put like this, and here I can put this. It will not make any difference. So if you look at the reverse relationship d by dx of fx, what do you get? It is 2x between x and 1, and it is 0 in the region x less than 0 and in the region x greater than 1. What happens at x equal to 0 or x equal to 1? It doesn't make any difference. Okay? That means you may include here or you may not include here. It doesn't make any difference. So again, the meaning of almost all is clear.
Yes, sir.
Okay. So let me take up a little more complex example. So fx is, it is defined to be x by 2 for 0 less than x less than 1, it is 1 by 2 for 1 less than or equal to x less than 2. It is defined to be 3 minus x by 2 for 2 less than or equal to x less than 3 and 0 otherwise. Okay, one thing I just wanted to show. Actually, in the case of continuous random variable, if I consider the plotting here, for example, 0 to 1, it is x square. So it is like this. Okay, this is the CDF. So there is no step function type of thing coming into picture. It is a continuous. Actually, for a continuous random variable, capital F is an absolutely continuous function. So it is differentiable almost everywhere. And if you look at the previous exercise here, yes, this one. In this exercise, how it is looking like? Up to here it is 0, and between 1 to 4 it is x minus 1 by 3. So you can do the plotting here. It is going like this. And say, let me four, and then it is going like this. So it is actually absolutely continuous function. In the discrete case, it is a step function. In the continuous case, capital F is a absolutely continuous function. So let me take a little more complicated exercise. So this is x and this is fx, small f. So between 0 to 1, it is this. Then between 1 to 2, it is constant. And then between 2 to 3, again it is this one. So this is the PDF. Okay, how the CDF will look like? Let us calculate it. So you look at the density function here. On the interval 0 to 3, it is defined to be some positive value, and outside this interval it is defined to be 0. So this will be 0 for x less than 0. Then for x between 0 to 1, it is integral from 0 to x, and the value here is x by 2. So this is t by 2 dt. Then between 1 to 2, it is integral 0 to 1 t by 2 dt plus 1 to x half dt, because that is the function defined here. Here it is x by 2 and here it is half. Then for 2 to 3, it is 0 to 1 t by 2 plus 1 to 2 half dt plus 3 minus t by 2 dt. So that is 2 to 3. And thereafter, sorry, this is 2 to x. And it is equal to 0 to 1 t by 2 dt plus 1 to 2 half dt plus 2 to 3 minus t by 2 dt for x greater than or equal to 3. So you can do the integration here. Is this step clear to everyone?
Yes, sir, it's clear.
So now it is a matter of integration. So for example, this one, if you look at t by 2, so integral will become t square by 4. So you get x square by 4. So like that you just write down. So capital F becomes 0 for x less than or equal to 0. Then it is equal to x square by 4 for 0 less than x less than or equal to 1. Then it is equal to 1 by 4 plus now next one is 1 to x. So that is x minus 1 by 2 for 1 less than or equal to x less than 2. Then next it is becoming 1 by 4 plus at 2 it will become half. So it is becoming 3 by 4. So it is 3 by 4 plus integral of 3 minus t square by 4 with a minus sign from 2 to x, and it is equal to 1 for x greater than or equal to 3. So this can be easily evaluated. You can evaluate it. See here, if you put x, then this is 3 minus x square by 4, and if you put 2 here, you will get 1 by 4. Okay, so it is 1 minus 3 minus x whole square by 4. So if you want, you can write like this: f capital F is 0 for x less than or equal to 0. It is x square by 4 for 0 less than x less than or equal to 1. It is equal to, now this you can combine here, it is 2x minus 1 by 4 for 1 less than or equal to x less than 2. And it is 1 minus, see this term I can combine here. If I put 2 here, I will get 1 by 4, which is with a plus sign. So it will become 1 minus 3 minus x square by 4 for 2 less than or equal to x less than 3. And when I take x greater than or equal to 3, then it is becoming 1. So this is the CDF here. Is it clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
And you look at the derivative now. If I differentiate in the interval x less than 0 and x greater than 3, I will get 0. In the interval 0 to 1, I will get x by 2. In the interval 1 to 2, I will get half. In the interval 2 to 3, I will get 3 minus x by 2. And for x greater than 3, I will get 0. The function is not differentiable at 0, 1, 2, and 3. Okay. So for almost all x, this is differentiable, and those points do not make any difference to this. I hope I have made the description very clear to all of you. Okay. At these 3 points only, the function is not differentiable. So let me give some examples. Okay. This is a CDF of which random variable? Can you tell?
It's a constant. Uniform random
No,
variable.
what is constant? Okay, uniform over what interval?
0 to half.
So 0 to half, what is the density function?
One.
1, sir. Not 1, sir.
If
2.
you have density
Sir,
function
2,
1
sir, 2.
on the interval
Fx
0
equal
to
to
half,
2.
then what is the total probability?
So it will be 2.
So how do you get 2? Because if you differentiate, you will get 1. You will not get 2.
But so if you integrate
If you
it back,
differentiate
then
x,
because like
if you
we know it's a
differentiate, you don't get 2, na?
No, that is true.
Yeah. So what is the answer?
Sir, answer though will be 2 because otherwise if we integrate it, it will not be
No, but
adding.
how do you get 2? Because if you differentiate x, you will get 1. You cannot get 2 there. If you differentiate x, you will get 1. How will you get 2? You cannot force it to be made 2. So what is the problem? Is there any problem?
Sir, there is density in one part and there is suddenly mass at half.
So this function is not continuous from right at x equal to half. Continue because we have mentioned that it should be continuous from right at every point. See, the right hand limit will be 1 and the value at x equal to half is half. So this is not continuous from right at x equal to half. So not a CDF. This is not a CDF. Okay. So I change it. Suppose I change it here. I make it like this. 0 for x less than 0 and it is x for 0 less than or equal to x less than half and 1 for x greater than or equal to half. Now it is continuous from right. Okay. Now this is continuous from right at every point. Is that okay? So can you tell what is this random variable? Can you tell what is this random variable? Yes, can you tell? Can anybody tell what is this random variable?
Sir, will there be a delta function in the distribution function at x equal to 1, x equal to half?
What is the meaning of delta function?
The thing that we have in physics, that integral of delta function from minus infinity to plus infinity is 1.
So what is the interpretation then? The interpretation is that you have density 1 between 0 to half and probability x equal to half is half. So there is a delta function what you are saying. Okay. So this is an example of a mixed random variable. That means it is partly discrete and partly continuous. On the interval 0 to half it is continuous, but at x equal to half there is a mass. So this is an example of a mixed random variable.
So that
If
would be 3 by
a
4, right?
random variable is, what is 3 by 4?
So the mass.
3 by 4. Why? Why 3 by 4? See, if you integrate from 0 to half, you will get half here, and then half is remaining. So this is, where is 3 by 4 coming in?
Sir, actually I got confused that this was density, sir. Sorry, sir.
This is the, again, this is again a mass. This part is a mass. Okay. So if a random variable is partly discrete and partly continuous, it is said to be mixed random variable. So for example, you have studied plasticity and elasticity of material, isn't it, in mechanics? So there is an elastic material, and you can, for example, you can put pressure, then due to elasticity, for example, you are pulling something, say a string, okay? So due to elasticity, it will keep on increasing. So there is a density there, okay? However, there is a certain stage after which it will break. That is a plastic stage. So if it breaks, then there is it is gone. So in that case, it is an example of a mixed random variable. Okay. For example, you put pressure on something, and the thing is getting, there is a thrust there. But if you put too much pressure, then it breaks. Okay. So there are examples of mixed random variables also. However, if you have a CDF, it describes completely that. Okay. Is this example clear?
Yes, sir.
Yes, sir.
Okay. Now let us move to the next topic. The concept of expectation. Okay. So we talk about this. Let x be discrete with EMF we define the expected value of x as expectation of x. So this is the notation. It is sigma xi into pxi. Provided the series on the right is absolutely convergent. This convergence condition we have to write, because if it is infinitely valued random variable, then the right hand side will become a series, infinite series. So it should converge, then only it will have a meaning. So let us look at some of the exercises. Is it clear?
Yes, sir.
Yes, sir.
In case of continuous random variable, expectation x is defined as integral x fx dx, and once again we put a condition of absolute convergence, because in case it is really infinite, then it could be improper integral, etc. So we need to have the convergence here. Absolutely convergent. Okay. So let us look at some of the examples here. So let us look at that sum on dice. Okay. So you had the random variables distribution. It was taking value 2 with probability 1 by 36. It was taking value 3 with probability 2 by 36. It was taking value 4 with probability 3 by 36. It was taking value 5 with probability 4 by 36. It was taking value 6 with probability 5 by 36. It was taking value 7 with probability, then it was taking value 8 with probability 5 by 36. It was taking value 9 with probability 4 by 36. It was taking value 10 with probability 3 by 36. It was taking value 11 with probability 2 by 36, and it was taking value 2 with probability 1 by 36. So you can add these things: 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12. So it is 252 by 36, that is 7. So now you consider the interpretation of this. So the sum on the two dice, it can be 2 with certain probability, it can take value 3 with certain probability, it can take value 4 with certain probability, and so on. Then expectation value is the value multiplied by the probability. Then what does it represent? It represents the expected value, or you can say average value. So when you do elementary statistics, then you calculate the arithmetic mean, isn't it? How do you calculate the arithmetic mean? You multiply the value by the frequency and divided by the total frequency. So in the case of discrete distribution, if you consider the frequency divided by the total frequency as the probability, then it is nothing but the arithmetic mean, isn't it? So if you again, so what does it mean? It means 7 is the something like a measure of central tendency, the average value. So if the outcomes can be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, then the average value is 7. Okay. Of course, here in this case it is middle value, because 2 to 12 you have even odd number, and 7 is the middle value. So let us look at the other exercise. Say you had this working ATMs. Okay. So what will be expectation there? You had probability, you had 0 with probability 1 by 10, you had 1 with probability 6 by 10, you had 2 with probability 3 by 10. So this is equal to 12 by 10, that is 6 by 5, that is 1.2. What does it mean? Do you mean that you can have 1.2 working ATMs? Of course not. You can have either 1 or 2 or 0. It is giving you a measure that where is the central value lying in, because you look at this, at 0 you had 1 by 10, at 2 you had 6 by 10, and you had 3, there you had 3 by 10. Okay, this was the way the distribution was defined. So if I just put it in a reverse way like this, 1 and 3. Okay, if we put like this 0, 1, 2, and suppose this is a weightless string connected to 2 points A and B, and these are the weights. So where is the point of equilibrium or the balance point? Then it is coming here 1.2. Okay, at this point there is a balance. Okay, at this point. Is it clear?
Yes, sir. Yes, sir.
Let us take continuous case also. In the continuous case, say fx is equal to 1 by 3 for 1 less than x less than 4. So OW means otherwise. Okay, so expectation of x will become integral x fx over 1 to 4. So that will become 1 by 6, and then you have 16 minus 1. So that is becoming 15 by 6, that is 5 by 2. So in this case, see, if you look at this one, it is 1 to 4. So 5 by 2 is the midpoint here. So this is the balance point. So if I am considering, say, if you look at this here, okay, this has a density, this is my pen. So if I am looking at the balance point here, so suppose this is tied on the two side with, say, string like this. So where is the balance point? So it may be somewhere here. Of course here the density is constant, so it is coming out to be the midpoint here. But if it is, the density is not constant, then it may be at another place. So for example, if I look at this one, this is another object here, and if I try to look at the balance point, then it may be something like this. Okay, so somewhere here it may come. So let us look at say for example this 2x for 1 less than x less than 2, for 0 less than x less than 1. For this, the expectation will become (0 to 1), so that is 2 by 3. So here the balance point is not the midpoint because the density is different. So that is why it is not the same. So let us consider this is another example. See here the density is 10 by x square for x greater than 10. So it is something like this. I should make it in a bigger area. Okay, so here the density is like this. So if for this one, if I look at what is expectation x, then 10 by x dx from 10 to infinity. So what it is? 10 log x from 10 to infinity, which is does not exist. It does not converge. Okay. This does not converge. So here expectation does not exist. Okay. In this exercise, expectation of x does not exist. So it may happen because here if you see this is unbalanced thing, like you are having this thing going up to an infinite value, but the balance will not be there. Okay. You can have another example. So let me give, say this is k by x cube, okay, x greater than 1 and 0. So k is some value. Can you determine what is k? So if you want to evaluate k, then integral of k by x cube dx 1 to infinity, this must be equal to 1 if it is a proper density function. So anyway, this integral one can do easily. So this is k, and you have integral of x to the power minus 3, that is x to the power minus 2 by minus 2 from 1 to infinity. So you get k by 2. Now you are saying this is equal to 1, that means k is equal to 2. So the density function then will become fx is equal to 2 by x cube for x greater than 1 and 0 otherwise. So what is expectation of x? Expectation of x will become integral 2 by x square dx from 1 to infinity. So this of course you can evaluate easily. So it is 2 and the integral is minus 1 by x from 1 to infinity. So that is equal to 2. So here the mean value is 2. Okay, or you can say if I am considering the density 2 by x cube, see 2 by x cube will be something like this. It will go like this. Okay, so the balance point is actually at 2. This is the thing. I have asked another question, what is the probability 1 less than x less than 2? Then this can be evaluated as integral 1 to 2 by x cube dx. Okay, so this of course you can easily evaluate. Okay, I'll leave this part here. You can just write down the value. What is the probability here? Okay. In the next class, I will talk about expectation x square, expectation x cube, the concept of variance, the median and other things. And then we will move over to specific probability distributions. You can see on this MS Teams, I have uploaded the assignment number 1 and its solutions also. Okay, so you please solve all those problems. You will have the regular tests starting from 2nd of February. So that is the first one, and then we have already decided about the tests, how it will be conducted. We have discussed. We will not ask multiple choice questions, but you will have to actually evaluate and write down the value. So for example, certain probability is to be evaluated, or certain expectation has to be evaluated, and we will be doing many other concepts actually later on. So it will be starting from the next week. I will stop today's class at this point. Okay. Is that clear?
Yes, sir.
Is it clear? Okay.
Yes.
So I will stop today's class at this point. Okay. Please solve the problems that are there. And I have been uploading the